So today we will be concluding our discussion of logistic regression. And so I have two goals today. The first goal is to explain what a loss function is, or what, in this case, what the maximum likelihood loss function is. And then two, I have posted a little IPython notebook to Blackboard that I want to walk through after we're done this theoretical, I guess, discussion of the logistic regression loss function. So what I thought I would do is start on the board. See if I got all my recording, screen sharing. I guess I'll make sure the projector is working. So the loss, like, I will present today the maximum likelihood loss function, but the importance of this, of the concept of a loss function, is much more than just logistic regression. Basically, all of supervised learning is in some degree, to some extent, maximizing some loss function. And okay, we good. Oh, MATLAB's gonna crash, but that's okay. This, don't need this yet. Definitely don't need that. Okay. So where we left off last class, or what we covered last class, is this form, this model, the logistic regression model family. So what I want to cover today is maximum likelihood, because it's, I mean, it's pretty widely used in machine learning, but it's kind of like a foundational statistical concept, and it's actually not as difficult to understand as definitely I thought when I first encountered it. Okay. So before we even get into the logistic regression problem, we have some data and we have a model family. So it's literally a family of models. Another way of thinking about it is it's a set of models. And then you have some data set that is typically denoted D. And in this case, our D is these are these called tuplets? I don't know, I think they're called tuplets. Pairs of XYs. And oh, I don't want to be sharing screen right now, I guess. Or do I? If I'm teaching on the board, I turn off share screen, right?
Yeah, otherwise all it sees is
It will see, yeah. Am I sharing screen? Can't tell. No, I'm not. Okay. Okay. So hopefully this is.
But maybe that's backwards for.
Yeah, but do you mind logging on and seeing if it's actually backwards on the?
Oh, I see that.
no try. Is it the same Zoom?
Yeah. Well, yeah, I can. It's always going to be the same Zoom.
That's it.
It's good. Okay.
Yeah.
All right. So the idea behind maximum likelihood is that you have a set of models and then you collect some data. And then you have to pick one of the models to kind of ascribe to your data. In other words, you want to pick the model that, and this is just in late, I haven't even given you the math yet, that best explains your data. So what does that mean? Another way of saying that is you want to pick the model that was most likely to generate what you observed. So the example that I always give is if I'm and there's probably a better example out there, but if I'm a genie and I'm cranking out Gaussian distributed random numbers, and every time you ask me for a number, I give you a number. So, I say, you ask me for a number and I say 2, and then I say 2, 3, 5, 2, let's say, right? And then I ask you, well, what is the most likely, given those 4 numbers, 2, 3, 5, 2, what is the most likely parameter of this genie? So what does the most likely mean? Well, what you will probably say is you would take the 4 numbers that you heard, 2, 3, 5, and 2, and they add up to 12. And you divide them by the number of times you asked me, which is 4. And you would say the most likely value of this genie's mean is 3, right? Because that's kind of a sensible, logical thing to do, because that guess minimizes the distance between what you saw and the possibilities, right? The answer could have been anything. It could have been a billion, but it's not likely that number was a billion. Otherwise, you wouldn't have observed numbers 2, 3, 5, and 2. And so it was the same thing here, where you go and collect some data, and then you have to figure out, there's some underlying model of your data. And so I think, so all models are wrong, but some are useful. So one thing that perhaps is misunderstood is that every model has some error. And by error here, I mean, there are certain things that the model simply cannot capture, right? But that's okay. And so in our case, the model is this very simple, well, actually, I'll put it here. This color. So this is our data, and the question is, what is our model family? So our model family in this case is the set of all possible weight vectors in the d-dimensional Euclidean space, where d is the dimensionality of x. So x is a d-dimensional random vector. And now for the sake of the maximum likelihood equations I'm going to derive here, we're going to say that our target variable is either +1 or -1. And so there's two kind of, and this is convenient for the logistic regression loss function, but oftentimes you see 0 and 1. It doesn't matter because this is the -1 doesn't actually mean anything. It just means different than +1. And so basically our model family consists of every d-dimensional vector W, and we have to pick the one that best explains our data. So what does that mean? So that means it's the one that, and this is the key, this is kind of the key thing that hopefully you can wrap your head around. You want to maximize the probability of your data given W with respect to W. So this is maximum likelihood, you know, in the most general sense. So the key thing here is that this is no longer, this is called the likelihood function. And the likelihood function is not a function of your data. It's a function of the model parameter W. So the data is now fixed. You've collected your data and it's not changing ever again. So this is not a variable anymore. What's a variable is a W. And so if W was one-dimensional, then the picture, you know, then you would have maybe some Gaussian looking thing. And this is probably, this will be the probability of your data. And then the model that you would pick would be here, because that value of W maximize the probability of observing what you actually observed, right? So this is placing a lot of truth into the data that you collected. Is it too early for iced coffee in the year? No. They're really upselling it, and I was wondering why is it that they're upselling their iced coffee so much? Even like last week, and I realized I know why, because they're more expensive. I paid $6 for this, whereas my hot coffee cost me $2 or $3, right? Why is it that iced coffee costs so much more?
Obviously, iced expensive.
No, that's definitely not it. You're actually getting less product in the iced coffee.
Cold brew takes longer.
This is cold brew, it is,
Cold brew takes longer to make.
but it's not more. You can't tell me that it costs 3 times as
It's
much.
like
Sure, that's
It's
not
a little more expensive for that much.
it's more.
But that's why they upsell
More
it.
labor.
Yeah, they don't actually care about whether I don't think they actually care about what I would enjoy more on this March day, cold or ice, hot or iced. They just want me to spend as much money, and that's why they have the beautiful, you know, beautifully like digitally altered photos of the foam, you know, in the ice cups. It has
I think
nothing
to
to.
acknowledge this, but you bought it anyway.
What's that? I did buy it. Listen, I have my limits, man. Yeah. But what did it surprise me that it was 572. All right. Okay. So maximum likelihood. So you want to pick the W that best explains your data. And so I'm going to, I used up way too much support. So I'm gonna try to hold up this. And so the key thing is you need some general form for your, you need some general form for probability of your data. And so in this case, given a single data point, xn, yn, this is, you know, your pixel of brain scan intensities, and this is whether it was benign or malignant. The probability that, this is going to be our model here. I actually think the notation is the only impediment to students understanding this. So our model is going to be this. So what is this, first of all, what does this mean before I convince you that this is sensible? This means that the probability that the truth is, so yn can either be -1 or 1, and x is just your data, and w is the thing that we're trying to optimize over. So if take yn is equal, take the case where yn is a malignant example. The probability that y is equal to 1, given that sample, right, is just going to be this, but this is going to be minus. Right, and now the probability in this equation for a benign example is going to be the same, except that the exponent is going to be positive. Okay, so hopefully I'll see that. So so basically what you're saying is that you're forcing, or you're trying to force all of your malignant examples and remember, you're going to be maximizing these. So you're forcing your benign and malignant examples to be on the opposite ends of that sigmoid. And that sigmoid we saw last time was like this. And so what this minus yn here does is it allows you to write your probability for both classes with one equation. And these are them. Okay, so now the next step then is to figure out how to actually, you want to choose your W that maximizes these terms over your entire data set. So I'm going to need, what is this? So you have, what you're given is some pairs of xn, yn, where xn is a vector, yn is either 1 or -1. And then you want to write, this is going to be called the likelihood function. And it's going to be a function of W. So it's going to be, in the most general terms, it's going to be the probability that you're gonna basically go through your data set times, because remember that we are always assuming that our observations are independent. And so I need to write an expression for the probability of that I would have observed the entire data set. So my data set has n independent sets, n independent pairs of observations. Okay, so this is a product of probabilities because these are all independent. And so if you have independent observations. So I have n examples. So every xn, yn is an example. And I need to write an expression for what's the likelihood that I would have observed all those observations as a function of W. And W is the thing that I don't know. W is the thing that I'm trying to find out what it is. Presumably there's some magic W that generated my data. Okay? And that's what you have to kind of believe. Now, again, in reality, especially for something like brain tumor data, this is too simple of a model to actually explain this. However, in many cases, it's good enough. And picking the best model from this family often does a really good job of classifying the data. So this can be written as a product. This is the product operator. Okay. So this is called the likelihood function. And so the key thing, if maximizing a function is the same as maximizing its log. And the reason that's true is because the log function is monotonic. So, and so first of all, why would I do this? What's wrong with just just trying to maximize this? Well, you could. The problem is that when you're gonna want to differentiate the p, and the p is this logistic function here, and so it turns out that for many functions, many models, maximizing differentiating it is harder than differentiating its log, and it's definitely true here as well. And actually, the original kind of idea behind it was that most probability functions are like e to the something, and the log undoes the e. So, for example, for the Gaussian, the exponent of a Gaussian is a quadratic, and so when you take the log of it, you just have a quadratic. So, that's why you get the you may have heard that maximum likelihood is often under Gauss. If you have Gaussian data, maximum likelihood is just least squares. They're equivalent, and that's because when you take the log of the Gaussian, you just get your least squares. Yeah.
What's J?
Oh, I didn't write a J, but my writing is really poor. Where's the J? Sorry.
Nine.
This?
An I in the sequence. An I in the brackets in the.
Oh, that's a semicolon.
Oh, the same
Yeah.
thing?
I
So-
thought it was a different.
Yeah.
Sorry. No. It's so this means, right, so this, I'm gonna try to make it. So this is actually this means parameter.
It's more of a J.
Okay, I don't know, man. You want me to maybe I'll just stick the comma. So basically, if you have probability of X, and you wanna be able to parameterize this probability, what they do is they
It's okay, I understand. I think something else.
so something like this. So basically what you're saying is that P is parameterized by W. It's not the argument of the function. That's the key thing. That's what the semicolon means. It's not an argument, it's a parameter of P. Again, mathematicians are pretty neurotic. Okay. They're like if you read any Wikipedia page nowadays, they've made it. Wikipedia started out as this really great thing because you could look up anything in math and physics, and you can get a pretty good explanation. And like people say these crazy things like, "Oh, Wikipedia is not accurate." It's pretty damn accurate for math and science. It's gotten to the point where now the hardcores have all gotten to the pages, and they've turned what could have been a really a good alternative to textbooks, which are over the top, filled with formalisms, and now they've made it just like the textbooks. Like if you look up a lot of Wikipedia pages nowadays, they're just like a textbook from the 50s. You can't follow it. And this kind of semicolon stuff is just kind of a relic of that. Like, yeah. Anyhow, it's not a J. I don't think there'll be a single J in this class. All right. So we said that we could just directly try to maximize this function, but I don't want to do that. I want to take the log first. There's two reasons for it. One is that it makes differentiation easy. Two is that it's going to convert this product into a sum, because the sum of a product, the log of a product is the sum of logs. And this is the really nice thing is now you have, instead of a product, you have a sum.
Is it log 10 or natural log?
No, it's a natural log. It's everything in this course is going to be natural log. No, actually, it was you who laughed at my semicolon. I should be asking you if the semicolon's okay for you. Okay, so this is now the thing that I want to maximize. So now I'm ready to plug in my general form. And my general form for P is this sigmoid function. So it's going to be 1 over 1 plus E. And so this is then the model that you go with, the W star, is going to be, I have some thoughts in a second about how you actually do this. It's going to be the W that maximizes this sum of logs. I'm going to write it as 1 plus E. This is going to be -1 exponent there. And so you are going to have to, or not you, but the functions all do this. So it's just, I just don't want to have to write another fraction. So the question is, how do you maximize that? The bad news is that it's not like with linear regression, there's a closed form solution. Like if you, for example, if you want to find the A that minimizes this, for example, then A actually has a closed form solution, and it's equal to the pseudo inverse of x times y, for example. Like you can actually write it's closed form. There's actually an equation that you can just plug in. That's not the case for this. And so I think I write this in the slide. There's no closed form solution to this function. And what that means is you have to employ iterative techniques or numerical techniques. And so we haven't covered gradient descent yet, but the idea behind gradient descent is, again, it's pretty intuitive. It's you have, you can, I'll try to see, are you gonna work? I don't think it's gonna work. So let's say your D is just 2 and you have W1 and W2. So you have some contours of your maximum likelihood function. And so this is the solution here you're trying to get to. And it's the top of the hill. This is a maximization problem. So you're climbing a hill. So you may start out here, and then what you do is you follow the gradient. And the reason you follow the gradient is because the gradient points in the direction of steepest descent. And so if it will look like as long as you follow the gradient, as long as you don't use too big of a step size, you'll always get to the top of the hill, basically. So that is that's what, when you call MNR fit in MATLAB, or when you call the function that I'm going to show you in Python in just a second, that's what they're doing. They're doing this kind of gradient descent procedure where you're starting off with a random guess, basically. You start off with a random guess for W, and then what you do is you evaluate the gradient at that point, and you go in that direction, and then repeat. Evaluate the gradient at that point, go in that direction. And so the gradient is a vector, so it has direction, it has magnitude. You don't really care about the magnitude here. You just care about the direction, because the amount of the step is a key parameter. You basically want to make it small, but not so small that your search takes forever. And so the basic idea is that the procedure here is to pick some initial guess for W, And usually people either start with the all zeros vector or a vector of small Gaussian random numbers. And then they run the search until this function stops increasing. Because at a certain point, well, the gradient becomes 0, hopefully, and then you just stop increasing, and then you know you've reached the top of the hill. So the hill is your likelihood function. You're trying to get to the top. Some intuition. So let's just consider one example at a time. So take the case of a positive example. You're trying to maximize, you want to push this to be, you want to push it to be as big as possible. So as close as possible to 1. So that means that the exponent there is going to have to be as positive as you can be. And conversely, if your examples from the negative class, you're trying to push the exponent to be very negative, right? Because you're trying to make this be 0. You're trying to make for every example that came from a benign class, you're trying to force the model to give a low probability of coming from the malignant class. And so I guess the thing to understand here is that this is a very clever approach to statistics, because you're basically saying it's different than just saying I want to make every malignant example p equals 1. I want to make every benign example p equals 0. You are doing that, but you're always keeping yourself to the form of the model. And so this model will make errors on a training set if that leads to a better model overall for all the data. So what I like about these kind of model-based parametric approaches is that they will make mistakes in a training set if it means that your data is well captured by the logistic function. I'll give myself maybe half an hour for the Python example. Let's see. We're going to cover there's okay. I'm just going to say one thing about a penalty term, because whenever you look up logistic regression, like in Python or MATLAB, you'll see this term a lot, penalty or regularization. So it's very, like in practice, you will never just directly minimize that, just the likelihood function. There will always be a term that looks like this. So this is called a penalty term. So what this term is doing is, two notes actually have to stay here. In practice, a lot of the software tools, they want to minimize. They do minimization, not maximization. So instead of maximizing likelihood, they will minimize the negative likelihood. And so, if you have a convex or if you have a concave function, I guess it's called, maximizing this is the same as minimizing its negative. So the likelihood function is like a concave function, and it's negative. So the negative, the likelihood, is a convex function, and all the software packages out there, they do minimization. And the reason I'm saying is I ought to correct this slide. There should be a negative term here, because J here is a cost function. So you want to minimize cost. And this is called a penalty term. And what it's doing is it's penalizing large values of W. And so it may not be clear why that would be a good idea to you. So the basic idea behind a penalty term is that you have some prior information about the model. And there's basically two types of prior information you can impose that I can think of. One is you expect your weights to be small and smooth, which is what that is doing. And two is you expect your weights to be sparse. So you expect many of your coefficients to be 0. And we'll cover that later on. And so lambda is called a hyperparameter. So it's a parameter you set, but it's not a parameter of your model. The parameter of your model here is W. Lambda is a parameter that's over top of that. That's why it's called a hyperparameter. And that parameter controls how strongly you want to impose this prior information. So the general rule of thumb is the noisier that your data is, the higher the lambda you want to choose. Lambda is something, if you make lambda very large, then you're going to force your optimizer to pick a weight vector that's very small. That's a very conservative approach because you're not allowing, like, you're essentially constraining. I should have kept that initial picture. That initial picture I had where I had all the families, all the model families, and every dot here is a model. Basically, what you're doing is you're constraining your search space to be just a subset of all the possible models. And so if you have, draw another picture. So again, keeping in this two-dimensional, if your feature vector only has 2 values, then you can represent this geometrically because your classifier only has 2 coefficients, W1 and W2. And the contours of this penalty term are spherical. And so what you're basically doing is you're only allowing, and let's say that you pick a lambda such that you're only allowing yourself to choose a model from this inner circle. And so those are going to be small w's. And the idea behind picking a small w is that it's less likely to overfit, really. A sign of overfitting is your coefficients growing very, very large in the training. So monitoring your coefficients is something that you generally do. And this is a way of penalizing very large weights. And the basic trade-off is that you have some training data. And if it's noisy, then you don't necessarily want to capture everything in that data set because you're actually going to capture some of the noise. And penalizing the magnitude of your weight vector is one way of doing that. It's preventing your algorithm from capturing all the little idiosyncrasies that are just kind of spontaneous in your data. So we actually have a whole lecture coming up about regularization and hyperparameters. I just wanted to give you a preview now because this is something that if you look at the documentation for the logistic regression function I'm going to show you, you're going to see these penalty terms show up, and I want you to know what they are. Okay. So does anybody have questions on anything we've covered before? So now I'm going to transition to, if I can get my Zoom back, I'm going to transition to the Python demo. So I'm actually wondering, I shared this IPython notebook, but I wonder if you guys are going to be able to open it. Has anyone tried to download it? Does it pop up? Can you show me what it looks like on your end? I've never actually done this in class. And I wonder if, so the other thing, you will need to have my cancer data set in the directory. You have it?
Yeah, so if it's in downloads, it'll be the same for you.
Yeah, right. No, yeah, I put it in I have like a teaching code subfolder that I put. So my cancer data set is also on the Blackboard. and we're going to use the same data set as we used last class in MATLAB, and I'm going to try it again to see if the Python and MATLAB versions gave us the same solution. Okay, so this is called a Python notebook or Jupyter Notebook, and what it lets you do, you're working in that. So this is, you can work in any browser, and you can essentially execute Python commands, and it doesn't have to be Python. I think that there's other types of scripting languages that you can use in these, but I've only ever used Python for this. So the idea is that these are cells, and in this cell you can either put code, or you can put a comment or a heading if you want. So if I switch this to Markdown, it will interpret this not as a line of code, but as a comment. And the thing about that is then when you want to use this as an educational tool, or just if you just want someone else to be able to read your code and follow along what you're doing, it makes it easy. And so the way this runs is you run one cell at a time. So I'm in my first cell here, and I'm just going to press run. And I'm going to actually give you guys, is everyone able to open this? Give you guys a sec. So the only, I think, constraint here, requirement, is that my cancer dataset.mat is in the same folder as you place this IPython notebook file. Foam is gone. Now it just tastes like regular black coffee. $6 black coffee. Okay. Import commands are something that you do in Python. You don't in MATLAB. Basically everything that's in your path, you can just call straight out of the box. In Python, it's a little bit different. Every function that you want to call, you have to explicitly import it. And so what I'm going to need, this means import a set of functions. Yeah, so I'm trying to figure out what the term. Scipy is a package, but .io is like a subset. I don't want to import everything from scipy. I just want to import actually the functionality to load the MATLAB data set. And so this is what I'm saying. I don't want to have to type. I could have written this function here as scipy.io like that, but I don't want to have to do that because that's a pain. I'm lazy. So I'm just gonna tell the compiler that SIO means that I'm calling a function from this package. Similarly, NumPy is the one like package that you will almost always import if you're doing any kind of scientific computing. NumPy is like Python's linear algebra package. It's great and it's universally used. So I need these two libraries, these two packages to run this logistic regression code. Next thing I'm going to do is I'm going to define my data file, the file that actually contains my X and Y. So I think I could, if you want to specify here, I think you can do, this means in this directory. And so you're telling the same thing as this. So you're just telling the interpreter that this mat file is sitting in the directory you're currently in, which happens to be the directory. It happens to be on my machine, it's the directory that I started the Jupyter Notebook in. So what I did is I navigated to the directory that had that data file, and I opened up Jupyter Notebook there. But you can do it, I think, through here. You can change your working directory inside the browser, I think. Okay, so what I'm going to do is now I'm going to execute this cell. And in programming, no news is good news. So if you don't get a message back, it means that it went through. And now we're going to see what went into data. So this means a load mat is just a function for, and there's also a save mat function. If you want to save data from Python into, or load MATLAB data into Python, or save Python data from use in MATLAB, you can use these load mat and save mat functions. And now we're going to see, I'm going to delete a cell. You just type DD, and then I'm going to insert a cell, and I'm going to type data. I'm going to run. And now when you enter a variable name and just press enter, it shows you the contents of that variable, of that object. So data here is what's called a Python dictionary. And a dictionary is just, it's a way of storing data such that all of your variables are associated with a string, with like a convenient label. So the elements of my Python dict are header, version, globals. Those are like, that's like the standard stuff. And then now we have in our data cancer inputs, and you can see that it's a two-dimensional array, right? Because you have the two. So in NumPy, and I haven't taught this, I'm kind of I haven't taught you NumPy, but I don't think it's going to be too difficult to understand the syntax here. But the idea is in NumPy, an array is encased with square brackets and commas separating the elements. And then if you have a two-dimensional array, it's like you're just nesting that. So if you have an array, a list of arrays, that's a two-dimensional array. Like if you have a concatenation of these square bracket arrays, it means that this is, this is row 1, this is row 2, row 3, etc. So the size of this array is going to be 9 by whatever, 700. We'll evaluate that in a second. And same thing for cancer targets. Cancer targets is an element of the Python dictionary. And it also looks like a two-dimensional array. So one thing I always do when I work in Python is I evaluate the shape. So the way to access data from a dictionary is to use square brackets and single quotes to point to the element of the dictionary that you're pulling out. So if I go, so this works. Right, so that's dot shape is something that I always do. It tells you it's MATLAB, it's the Python equivalent of size. So this means that the shape of the variable that I've selected here is 9 rows and 699 columns. And so the 9 are my features, and the 699 are my examples. And I can do the same thing for my target variables, my label.
Is there a way to put like comments?
Comments, yeah. Let's say I go insert above, and then I go markdown, and I can say this is a comment, and then run. And then there's also like, you can change this to be, I don't know what this is. Maybe one of you know. Yeah. Oh yeah, if I just put the numeral, it will automatically convert it. So I don't know what this is though. And so the thing about this is that this is HTML. And I think the main reason why people love this so much is because when they write their blog posts, like I will occasionally read like towards data science and stuff like other like kind of blogs about data science, and they do things like this. They'll have text, and then they'll have a block of code, then they'll explain it, and then so Jupyter makes it easy to do things like that. The one thing that this doesn't have, but I will show you an editor in Python that does have it, is it doesn't have the variable explorer. Like in MATLAB, you have on the right, you see all your variables, and you see what their values are, which is very convenient when you're doing scientific computing. So I don't think Python originated for scientific computing. I actually think it originated for software development, and that's why it's a little bit less convenient for research, kind of research that we do. Anyhow, let's look at, and if we want to print the shape of cancer, let's see if this will work. Let's see if this will work. No.
We're trying to print.
There's some, what's the string conversion? Hold on, see this one. So you can actually,
We can use comma and the data frame plus str.
so the plus sign is, I think MATLAB's now trying to copy this and they've come out with their own.
If you put comma, it is it's gonna be like comparable with numbers.
If I put, you mean like this? You sure?
You don't put str.
Oh, you don't put str? Okay, let's see.
I think so.
Yeah, very nice. There you go. So this, you want to look at the shape of your data. And if you want to actually, if you want to look at what your data looks like, you have to, I guess you need, if you want to look at your data, you have to hit the variable name and enter, then it will show you. And again, this is, these are the first 3 rows and the last 3 rows of your X. So I'm assigning the inputs to my X, and I'm going to assign the labels to my Y here. And notice that the shape of Y, show you all the steps. The shape of Y is going to be 2 rows by 699. And the reason for that is that, remember, the data came in as like almost probability. So if in row 1, this is the probability that that example came from the benign class, and row 2 is the probability that it came from the malignant class. And so, for example, if we want to print out all the rows, but the first 5, the first 4, shouldn't this? First 5, I guess you have to do this. These are the first 5, labels of our data set. So remember, if you remember last class, the first 3 are benign, then we have a malignant, then we have a benign. Okay, so now we want to pass this data to Python's logistic regression, and there are several implementations of logistic regression. I'm going to show you the one that is probably the most commonly used. It's from a very popular library called scikit-learn. And so scikit-learn has a logistic regression function or class. It's actually a class. And I'm going to import it here. And so I'm going to execute this line. Nothing's going to happen, which is good. And then I'm going to just instantiate. I'm going to create a new logistic regression model. I haven't done anything yet. So at this point, I'm just telling Python that model has nothing in it yet, but it will be a logistic regression model that I'm going to assign some data to in a second. So if you actually look at the help of scikit-learn, So this is, it's pretty well documented. But what you will see is that their fit, we're going to need to call the fit function. And I'll show you. Blah, blah, blah. We're going to need to call the fit function. And what you're going to see is that, and this is going to be universal to Python, it expects your data to be in the form samples by features. So samples on the row dimension and features on the column. The problem is that the data that we pulled in from our data set is the other way. It's transposed from that. It's remember, it's 9 by 699. Oh, this is. It's 9 by 699 and 2 by 699. Scikit-learn, this logistic regression family, logistic regression function, needs the data, first of all, needs X to be features by, sorry, but it needs to be examples by features. So I'm going to call the NumPy function transpose, which is exactly what it says. So it's going to take our 9 by 699 matrix, make it 699 by 9. It's going to do the same thing for Y, but in addition to that, it doesn't want a two-dimensional label. It wants just a one-dimensional array of the labels, and it's calling the labels targets. And so what I'm going to do is I'm going to take, it looks like I'm taking the first dimension, but I'm actually taking the second dimension here because Python is indexed from 0. And so this means transpose Y and then extract only the second row from it. And then, so if I execute this, execute that, you see that now my, what I'll do is print out Y, and you'll see that now our label vector YY is a scalar. So it's a 1D vector, and the values are either 0 or 1, and they're 1 every time you have a malignant example and 0 for every benign example. And you can do things like NumPy mean YY. If you want to know how many of each class you have, you can do this. So you have 34% of your examples are from the malignant class. Okay, so this line here is the key one. This is where you actually give the data to your model, and B, you actually fit your logistic function. And so I actually don't know if I needed to put in model equals model.fit, but I did it just in case. MATLAB and Python are pretty different in the way they pass data. So I believe if I do this, that after I do this, my model will, I'm not sure actually. Let's see. Yeah, no, it still works. But I did it just in case because I wanted to make sure that after calling this function, that the model weights are now in my model object. So model is an object. An object is like, think of it as like a set of variables and potentially functions. It's a way of it's a way of combining different types of data into a single entity. And so what this says is call the function fit from class on object in object model on the data x, x, and y. And what this does is, and notice how quick it was like lightning fast. I think the MNR fit takes significantly longer. So now my model, I try to see if it would print anything out. Oh. So I'm gonna, just to convince you that it did do something, I'm gonna print out the coefficients that it learned. And so you see it learned 9 coefficients. What I'm gonna do is I'm gonna initialize it. Print out at the beginning, after here, this should be empty. We'll see if it is. Oh, it doesn't have coefs yet. Okay. So it doesn't even, I guess it just makes an empty, I guess it just makes an empty object. And the point is that at this, after this line, there's no coefficients yet. The coefficients only appear once you give the data and you call the fit function. So fit means learn. So these are your, these 9 elements are your 9, the elements of the vector of the W vector, which classifies your, which is going to classify your data. And there's a second function, there's another function called predict underscore proba, which means predict. What it really means is figure out what the probabilities are of every feature vector in XX. So I'm going to call this function, I'm going to call this on my data, and I'm going to print out what the model predicted for every example. So this is in scientific notation, which makes it a little weird, but this is 0.98 and this is 0.012. So for the first example, the model thinks that the example came from the benign class, which it did. Right? This is, keep in mind, this is the training set. And so it's going to do a good job because we're learning and evaluating the model in the same data. And if you want actual predictions in terms of 0 and 1, you use the predict function. And if you print out YY hat, you see that it prints out the predictions of your model on the data that's in XX. And so now you have the ground truth, which is YY, that's here. And you also have your model predictions YY hat. And I want to know what the accuracy is of my model. So I do a mean operation of this logical expression. So this says if YY hat matches YY, this evaluates to a 1. And if it doesn't match YY, it evaluates to a 0. And so you see that on our training set accuracy is 96.6%. And I don't remember, I'm going to go back in a second and see what it was for MATLAB. But if I look at the weights, and I'll show you how to plot them here. So there's a very popular Python package called matplotlib, which lets you make plots directly in the editor. And so this is what our coefficients look like. And coefficients 1 and 6, or this index from 0, have the largest weight. So if memory serves me right, I don't think this is what our weights look like in MATLAB, but I'm going to run it quickly and compare. But I think the accuracy was very similar. 96.8? 96.85. Where is it? Ugh. Did I not put it in? Give me a second here. What did I do? I took out some dimension. Right, 96.8. But I think that the weights look very different. That's all, yeah. Well, that's what are the weights called? B. the negative means that I just, and now let's compare this. You can put this side by side. So they are definitely different. What's that? Yeah. Yeah. That's so I suspect that, and again, it's yeah. I've done some work for our company recently where we had to port code from MATLAB to Python, and one of the exercises was as a sanity check to make sure they're giving the same result, and it's actually much harder to do than you would think. There's a bunch of, first of all, the random number generator there's a random number involved here. When you fit your data, you're doing that iterative procedure, and so they will start at a different spot. That's one thing. But I think the bigger thing is that Python scikit-learn will, yeah, regularization is applied by default. So I think that if we set, I'm not going to do this now because I'm out of time, but I think if I set my regularization to just be off, I think we would get very similar results. But well, basically, the thing that I wanted to demonstrate this week, last two lessons, is basically the 3 core steps that you take when you want to learn a model. The first step is to curate your data, get it into the form that your function needs, and we did that. Where do we do that? Where's those transpose steps? Here. We did that here, and then there'll be a function. Then there'll be a call to the fit function, which is here, and then there'll be a call to a predict function or an eval. This would either be called predict or evaluate or test, something like that. And those are kind of the 3 steps that you're always doing. And that's the basic workflow for machine learning. The only difference is how sophisticated your model is. Logistic regression is a really good baseline. So when you're starting out with a data set, the first thing that you always do is run it through something like this just to see how clean your data is. Okay. And